Welcome to Lecture 3.5, Rational and Irrational Numbers. Much like the previous lecture, most of the content in here is probably not going to be new for you, but we're doing it because it's important to see how to formalize basic mathematical concepts and prove some fundamental theorems. Let's get started. A real number r is said to be rational if it is the quotient of two integers. In other words, if r equals a times b for some integers a and b. Otherwise, it is irrational. Now, many books and sources will require that b be non-zero, but I think that's unnecessary because if r is the quotient of two integers a over b, then it must be the case that b is non-zero. So I don't think we need to build that into the definition, though it's certainly not wrong to do so. Let's do some examples, though I won't prove all of these. To begin, every integer is rational because n equals n divided by 1. The sum of two rational numbers is rational. I'll actually prove this on the next slide. Every decimal that terminates is rational. For example, 1.234 is just 1 plus 234 over 1,000, or just 1234 divided by 1,000. Not a proof, but an example that should illustrate how a proof would work. Every repeating decimal is rational. This is a little bit less obvious, but you've probably seen it before. I will not prove this, but again show you an example that should make the technique clear. For example, if x equals 0.121212, etc., well, it's not clear what to do with this, but I'll give you a hint. If you multiply x by 100, then you get 12.121212, etc. So why is that useful? Well, if we take 100x and we subtract off x, then we actually get an integer 12. So 99x equals 100x minus x, which is 12.121212, etc., minus 0.121212, which is just equal to 12. Okay, so what good does that do? Well, it actually gives us an equation. 99x equals 12. So x equals 12 divided by 99. And in general, when we have a repeating 0 point something that repeats, this ends up being that something over some number of nines. And you can modify this technique to show that. Finally, the numbers square root of 2, pi, and e are all irrational. I will prove later in this lecture that root 2 is irrational. We will not prove that pi or e are irrational. I will leave you with an exercise to show that every repeating decimal is rational. Now, I did outline the technique above, but I encourage you to pause the video and give it a shot on your own to write that up into a coherent argument. Now, as promised, I will prove a few basic properties about rational numbers. And once again, the main point here is not the actual properties themselves, because I'm confident that you already know these, but how the techniques go. The first one is that if r and s are rational numbers, then r plus s and r times s are also rational. So these are really two things. I mean, here I'm trying to show if r and s are rational, then r plus s is rational. And if r and s are rational, then r times s is rational as well. So with any of these, it's always good to right away think about how you want to prove this. Do you want to do a direct proof or an indirect proof, like by contradiction or contrapositive? So let's check this. So if r and s are rational, that means we can write these things as fractions. So we can write r maybe is a over b, and s is c over d. then just using the basic properties of how to add fractions, we can certainly write the sum as a fraction as well. And we can also write the product as a fraction. That's straightforward. Just for a mental exercise, let's think about what it would take to prove the contrapositive, or do it by contradiction. So to do that, we would have to somehow assume that r plus s is irrational. And that's really hard, because there we're basically saying there is no way to write this number as a quotient. So where do we go from there? There's not really anything we can do. So a lot of proofs, as we've seen, and we'll see more, one of the directions is straightforward, and the other direction is basically impossible, because we don't know how to work with the fact that r plus s is not rational. Okay, so moving on to the second proposition. If r is rational and s is irrational, then both the sum and the product are irrational. Think about how we're going to prove this. So here, if r is rational and s is irrational, then I'll write it like this. Then r plus s is irrational, and r times s is irrational. So here, going directly is going to be actually hard. Let's think why. So if r is rational, then once again we can say that r equals a over b, but s being irrational, we don't really know how to write s. So we don't really have a good grasp as what to do. And also, even if we did, how do we prove that r plus s is rational? So it's much more natural here to assume, or to do this one in reverse. In other words, to prove the contrapositive, or do it by contradiction. Contrapositive is a little more direct. So assume that the conclusion is false. In that case, r plus s is rational, which means we can write it as a over b. And then, if that's the case, let's show that one of these things has to fail. And similarly with this one. Okay, that's the second one. So once again, the main insight here is the proof technique, and how sometimes it's, when is it better to do direct proof and when an indirect proof. The third one is if r and s are irrational, then, I'm not going to tell you the answer for this one, I'll let you think about it. R plus s, is it necessary? It could be irrational. Does it have to be? What can we say? Okay, let's prove these. For the first one, I've already outlined how to do it, so let's write it down. Let's let r be equal to a over b, and s be equal to c over d. Then r plus s equals a over b plus c over d, which is a d over b d plus bc over bd, which is ad plus bc over bd. And the important thing is that this is rational. And also that b and d are non-zero. So this is indeed a fraction, a rational number. Also, r times s is a over b times, well, I'll just write ac over bd, and this is rational as well. Okay, so there's the first one. I should maybe write that. The second one, we're going to do by contrapositive. So there's really two of these. The first one is that r is rational and s is irrational, implies that r plus s is irrational. So let's do this by contrapositive. So let's say that r plus s is a over b. Okay. And then we want to show that this does not hold. That's a little tricky. So let's actually change this to contradiction. Let's So let's assume that the negation is false, or not the negation, let's assume that the conclusion is false, and these things are true, and let's come up with a contradiction. Okay, so I wrote counterpositive, let me say contradiction, because that just seems a little more natural, because it's hard to negate this and statement. I mean, I guess you could. It really is logically the same thing. Okay, so let's suppose that R plus S is A over B, and that R is C over D, and S, well, actually, I don't know what to say about S. So let's just start with this, and let's conclude that S is rational, and that will be the contradiction. So actually, what I can say is I can say S is irrational. Okay, so now what? So S is R plus S minus S, which is A over B minus C over D, and this is AD minus BC over BD, and this is rational. So this is a contradiction. You know, we didn't have to do this by contradiction. I could have said, suppose this was false, and then if R is rational, then this has to be rational as well, which means the assumption is false. Either of these work. But however you do it, it has to be indirect. Finally, the last one. If R and S are irrational, then what about their sum? Oh, actually, there's one more I haven't done. I haven't showed that R times S is irrational. Let me do that one now. Let me call this part B. Okay, so for part B, we're going to have the same assumptions. R is rational, S is irrational. And we want to conclude that RS is irrational. So let's, once again, do a contradiction and assume that R times S is rational. So let's say that R times S is A over B. Oh, and I should also say contradiction. I said it, but I didn't write it. So for sake of contradiction, assume RS is AB, and R is C over D, and S is irrational. So we can't really write that as anything. But if we can use these assumptions and show that S is actually rational, then we have arrived to our contradiction, at our contradiction. Okay, so how do we do that? So we want to come up with an expression for S. So S is, well, let's take RS and divide it by R. So S is RS divided by R, which is A over B times the reciprocal of C over D, which is D over C, and this is rational. So there is our contradiction. Are we done? Well, let's check. Here we have to actually assume or verify that the denominator is non-zero. Is that true? Well, B is non-zero, right, because R times S is rational, A divided by B. What about C? Well, C is the numerator of R. There's no reason why C has to be non-zero. So is that a problem? So RS divided by S, if R is 0, can't really do that. I mean, we kind of want to, but let's check. So what happens if R is 0? What goes wrong? So if R is rational, say R is equal to 0, and S is irrational, then I claim that RS is irrational. That's actually not correct. Remember I said that not everything in here is going to be correct. So yes, what I'm trying to prove is actually wrong, and this happens sometimes. You try to prove something and it's either flat out wrong, or sometimes there's a little detail, like the 0 case, that you didn't take into account. So let's modify this. So if R is rational, I say if R is rational, and R is non-zero, if r is a non-zero rational number and then s is irrational, then yes, then this proof goes through, and then we can say this is a contradiction. Okay, finally, for the third one, if r and s are irrational, then r plus s is what? Well, it seems like if you take two random irrational numbers that you should probably get something irrational, so something like root 2 plus root 3, or root 2 plus pi should probably be irrational. And we don't know how to prove that. I'll show you how to prove something like this soon. But with a little more thought, well, since we really don't know how to prove this, I mean, I guess what we could try to prove is the counterpositive. We could say, suppose r plus s is rational. Suppose r plus s is a over b. And how do we prove that r plus s are irrational? So I guess you would have to somehow negate that. So the negation of this is that one of these is rational, but that also seems hard, because what if only one is and not the other? Okay, so sometimes if you don't know how to prove it, it's worth trying to break it. Are you sure this is true? Can we find a counterexample? And actually, with not too much thought, we can. So this is actually false. For example, root 2, or let's suppose r is root 2 and s is negative root 2. Right? And then r plus s is equal to 0. Now, I haven't proven that root 2 is irrational. You can take that for a fact. I will do that later in this lecture. Okay, let's move on. Let's now prove what I claimed on the previous slide, that root 2 is indeed irrational. The proof of this dates back to the ancient Greeks in the 5th century BC. They were the first society to study math for math's sake, for the intellectual beauty of it rather than for its utilitarian sake, for example, to navigate when sailing a ship or other many purposes. And actually, it was quite controversial when it was proven, because the ancient Greeks believed that numbers were rational. Everything was rational. That irrational numbers did not exist, and legend has it that the man who discovered that root 2 was irrational, or at least who leaked the proof of that, was murdered for it, though it's not clear whether that was actually true or if it's legend. So this was something that the Pythagoreans, a secret that they held from the outside world, because in some sense they were ashamed of it. They didn't want to admit it. So let's see how they did it. How do we prove that root 2 is irrational? Once again, we can't really prove this directly, because how do you prove that something is irrational directly? You sort of have to assume that it is rational and arrive at a contradiction. So let's do that. So for sake of contradiction, let's suppose that root 2 equals a over b. And also, this is not an a implies b type proof, so there doesn't really make sense to talk about the contrapositive, because this is not an if-then statement. So we really have to assume that it's false and break the universe. So suppose root 2 equals a over b. Then what? Well, then we can say that, well, what do we want to say? We want to say that a equals root 2 times b. Okay, that's great. Then what? Well, then we can square both sides. A squared equals 2 times b squared. So where's the contradiction? Let me first explain it to you, then I'll try to write it out a little more formally. So if you assume that every number can be factored uniquely into primes, which is something that we did, then the number of primes that appears in a square for any prime is going to be even. So, for example, if a equals P1 E1 times P2 E2 all the way up to PK EK. Then A squared is going to be P1 to the 2 E1, P2 to the 2 E2, etc. Point being that these exponents are all even. So how many times does 2 appear as a prime factor in A squared? Well, it's an even number of times. However, the right-hand side, 2 appears an odd number of times. It appears an even number of times in B squared, but then one additional time right out front. So that's basically it. Now, I think it's fine to say the number 2 appears an even number of times in the prime factorization of A squared, but an odd number of times in 2B squared, because an even number of times in B squared and then one more time out in front. And so this is a contradiction. This is a contradiction. So this is absurd, as the ancient Greeks would say, and therefore our original assumption must have been false. So root 2 cannot equal A over B. And that's it. Now, it's worth mentioning that many, if not most sources, won't actually stop here. They'll be a little more picky on this, and I don't think they need to, but I think it's worth mentioning what their arguments are in case you encounter one of these. So we can assume that root 2 is A over B, and something else we can also assume is that the GCD of A and B is equal to 1. So they have no common prime factors. And in this case, we get down here, we say that this is even. 2b squared is clearly even because 2 is even. And so therefore, A must be even as well. So since 2b squared is even, so is A squared, and so is A. So if A is odd, then A squared is odd. So A has to be even. So if A is even, then A is 2 times C for some integer C. Then let's take this equation up here. A squared is 2C squared, which is 4C squared equals 2B squared. And now this equation we can divide by 2 and we get that 2C squared equals B squared. And once again we can make the argument that 2C squared is even, and so B squared must be even. So let me write that down. So B squared is even. By the same argument above, I'm not going to repeat that. Hence, B is even. But now we have the case where A is even and B is even, and we assume that they have no common factors. Well, if A and B, no common prime factors. If A and B are both even, then 2 is a common prime factor. But this means that 2 divides A and 2 divides B, and this contradicts that the GCD of A and B, the greatest common divisor, is 1. Okay, so once again, I don't think that's necessary. I think proof is a convincing argument, and this ending here is absolutely a convincing argument, but I do mention it because I think most sources actually go this extra step, though I personally deem it unnecessary. we'll conclude this lecture with discussing how to prove related statements, like root 3 is irrational. So we don't need to prove this separately, and root 5 is irrational, and root 7, and so forth, because there's infinitely many things to prove. So the technique is completely analogous. So if we were to prove this directly, we would have to assume that root 3 is a over b. And so once again, a is root 3b. So a squared equals 3b squared. And come up with a contradiction because the number of times that 3 appears as a prime factor on the right-hand side is odd, and on the left-hand side is even. And this works for not just root 3, but also for root p. So suppose that root p is a over b. So we can do exactly the same thing and get that a squared equals p b squared. And I claim that actually we can not just use prime numbers, but we can use any number. So actually I claim that root n is irrational if and only if n is not equal to k squared for some integer k. Now, so that means we have to prove this, we have to say, suppose this is true, and root n is irrational, then n is not a perfect square. So let's think why that's true. So if irrational, then not a perfect square. Well, that makes sense, right? Because if do that by contradiction, if n is a perfect square, then root n is clearly not irrational. It is actually an integer if n is a perfect square, like 9 or 16 or 25. So that's actually trivial. The hard part is showing that if n is not a perfect square, then root n is irrational. So I'm not going to prove that for you, but I'll show you how it works just with an example. So let me do an example. Why is root 6 irrational? So this is a little harder because it's not just a single prime. But let's say that root 6 equaled a over b. Then once again we can write 6 equals a squared over b squared. So a squared equals 6 times b squared, or 2 times 3 times b squared. So we arrive at the same contradiction by taking either one of these primes, 2 or 3, and showing that. And so you just take for 2, that appears an odd number of times on the right-hand side and an even number of times on the left-hand side. Okay, so let's move on. I think we've beaten that horse to death. Let's prove that root 2 plus root 3 is irrational. This one is a little harder. It's not clear how to proceed. So, well, let's suppose we have to do this again by contradiction because there's no if-then statement. And we can't really do it directly because how do you prove that something is irrational? So let's suppose that root 2 plus root 3 is a over b. So in other words, it's rational. Then, well, root 2 plus root 3, let's square that and see what we get. This is 2 plus 3 plus, is it root 6 or plus 2 root 6, isn't it? Yeah, 2 root 6. So this is 5 plus root 6. So now 5 is rational, and so if this is rational and 5 is rational, then it must be the case that root 6 is rational. But of course we've argued, haven't written up formally, but we've argued why that can't be the case. So together they show that root 6 is irrational, which is a contradiction, and sometimes we use this symbol, I don't remember if I told you that, for a contradiction. This is one of many symbols that we can use for a contradiction. Okay, so that's how this goes. And finally, how do you prove that the cube root of 2 is irrational? Well, let's once again suppose that it's not. Suppose that it is rational, so it's a over b. Then we can cube both sides and get that 2 equals a cubed over b cubed. And now we get 2b cubed equals a cubed. And we can do a similar thing, a little different, by counting the number of times that 2 appears as a prime factor on the left-hand side. Now it's no longer even versus odd. It's the number of times that 2 appears as a prime factor on the left-hand side is not a multiple of 3, but it is a multiple. It appears some multiple of 3 times on the right-hand side. So there is your contradiction. I will let you, I'm not going to finish writing it up. I will let you do that for practice if you so choose. Okay, so next finishes that lecture. Next time we will discuss quotient, remainder, ceiling, and floor, and the division algorithm. And then from there we will discuss the Euclidean algorithm, which is basically a quotient and remainder algorithm. It's something that you do all the time when you do long division and take a remainder, but it's extremely important because we want to do it algorithmically because we will be using it later in the class when we study cryptography. So stay with us. We'll see you then.